All right, let's dive into a topic that has captured our imaginations for, well, forever. We're talking about something straight out of sci fi, something from fantasy novels, the power of invisibility.
I mean, you know the scene, right? The spy hits a button on their suit and poof, they're just gone.
Or maybe it's a wizard pulling a shimmering cloak over their head and they just fade away piece by piece.
Or how about this one? A pilot in a starship flicks a switch and the entire vessel just vanishes into the blackness of space.
It's gotta be one of the coolest powers imaginable. But here's the real question, the one we're here to tackle. Could this fantasy ever become reality? Could science actually figure out how to make the visible invisible? To answer that, we have to jump from the world of fiction into the world of physics. Now, look, we already have some incredible stealth technology that can hide a plane from radar or a tank from thermal cameras. But making something invisible to the human eye? Whoa, that is a whole different ballgame. And it's way, way harder. So here's the absolute heart of the problem. The only reason you can see anything, me, the chair you're sitting on, anything, is because light waves bounce off of it and hit your eyes. So to make something truly invisible, you can't just block the light. That would just make a shadow. No, you would somehow have to make the light from behind the object, travel around it, and then continue on its path to your eyes like nothing was ever there. You literally have to reroute light. Okay, so how in the world do you reroute light? Well, you could try using mirrors, but the angles would have to be impossibly precise. You could try absorbing all the light with a super black material, but that's not true invisibility either. So that brings us to the most promising idea of all, actually bending the light. And there's a scientific principle for that. It's called refraction. Refraction is really just the fancy term for what happens when light changes direction as it moves from one type of material into another. The classic example, light moving from air into water. And you have absolutely seen this happen. Have you ever been sitting at the edge of a pool and looked down at your legs? They look all bent and kind of broken, right? Well, that's it. That's refraction happening in real time. The light traveling from your legs moves through the dense water, and when it hits the less dense air, it speeds up and bends. Your brain is literally being fooled by physics. But here comes the catch. In nature, there are hard limits. Even with materials that are really, really good at bending light, you just can't bend it far enough to make it flow completely around an object and come out perfectly on the other side. Nature's rules just don't seem to allow for it, or at least that's what we used to think. And it's right there, at that very limitation, that a huge breakthrough happened. Back in the 1990s, a physicist named John Pendry was actually working on something totally different, how to absorb radar signals. But what he discovered was about to change everything. See, while he was working for a defense lab, Pendry created this special carbon fiber mesh that was so incredibly thin and tightly woven that it started interacting with light waves in a way that normal materials just couldn't. This sparked a revolutionary idea. What if you could engineer materials at the microscopic level? What if you could add tiny, tiny structures to give them brand new powers? He called this new idea metamaterials. So what are they exactly? Well, metamaterials are built with structures that are actually smaller than the wavelength of light itself. And because of that, they can do things that are flat out impossible in the natural world. Things like achieving negative refraction, which basically means bending light beyond its theoretical limit. This one single discovery kicked off the entire modern search for invisibility. And using this exact technology, labs have actually done it. They've made metamaterials that can steer microwaves completely around an object, making it invisible to radar. But, and this is a huge but, microwaves are one thing. Making something invisible to all the colors of visible light that our eyes can see, that is a whole other beast. Yeah, this really puts the problem into perspective. A true invisibility cloak has to perfectly bend all the colors of visible light at the exact same time. The problem is, that's not how light works. You know how a prism makes a rainbow? It's because it bends each color of light by a slightly different amount. Well, a metamaterial cloak runs into the exact same rainbow problem. It struggles to bend red, green, blue, and every color in between all in perfect sync. Now, even with that big challenge, metamaterials are definitely the frontrunner. But they aren't the only game in town. Scientists are exploring some other pretty fascinating, if a bit wild, ideas to crack the invisibility code. So let's run through the competition. First, you've got the mirage effect, which uses superheated air to bend light. but you need thousands of degrees of heat, so, not exactly practical. Then there's a clever setup using glass lenses, but it only works if you're looking from one very specific angle. Move an inch and the illusion is shattered. Finally, there's the high-tech route, using cameras to project the background onto a cloak. It's a cool idea, but it suffers from lag and the colors are never quite right. So as you can see, every single one of these methods has a major catch. When you look at all these different efforts, it's pretty clear we still have a long way to go. For now, a true invisibility cloak is still firmly in the world of science, not quite science fiction. But the whole story of science is about overcoming what seems impossible. Because with new materials, new breakthroughs, and new theories, the things that seem impossible today often become possible tomorrow. And that's a really powerful thought. The very limitations we see today, they could one day simply disappear. And that leaves us with one final, pretty provocative question. If we do solve this puzzle, if we perfect this technology and create true, effortless invisibility, what would that world actually look like? What would we do with it? That's something to think about.